Good morning, friends. I am Abhijit from IIT Madras. We are going to have a 5-hour session overall in engineering mechanics, and in particular, we'll talk about particle kinematics. Um, so, here's the table of contents. What we are going to cover in these 5 hours. Rather, as one of my teachers used to say, we are going to uncover these topics for you, and they are as follows. Today, we are mainly going to deal with this part of the course, which is clarifying a few words that we keep hearing in this subject. That's we're going to discuss mainly the nomenclature and set ourselves up by the discussion of different types of motion that we are going to analyze, and a very crucial aspect would be the different coordinate systems that will be used in the analysis. So let's go forward. These things will be covered in due course. Let's not waste much of today's time on it. Fine. So here's an invitation to dynamics. Dynamics is a very foundational level subject. It is something which is all pervasive. It is ubiquitous. So there is hardly any application where you don't see the use of dynamics. Dynamics is there all around. So it's good that if we could study this subject of dynamics with some effort in our foundational years, so that later in the applications we should not have any problem in dealing with this subject. And the best thing about dynamics, unlike some other subjects, is that there are only very few rules to remember, and the purpose of this talk is probably to emphasize these very few simple rules. And the way I have been taught dynamics and the way I teach dynamics to my students is that we should not worry too much about the formula. The formula will come by itself, and also maybe in stark contrast to what some of you think, the way I think in this about this subject is it's not really a big deal to solve different problems by plugging values into a memorized formula. What is most important is the action of understanding the rules of the game, understanding the concept, and then applying it to every situation. I would rather discourage you to practice too many problems from routine books which are just going to use some formulas and how to use some formulas in particular problems. That is something which at least for me I think is not a very good idea. So going ahead, let's start with the course in proper. So as we said that the topic that I am going to cover in this set of 5-hour lectures is particle kinematics. So I begin with the following description, that what does these the two words namely particle and kinematics mean. So I'll spend some time in uncovering these ideas to you. To start with, what is particle? So it may appear to you that by the use of word particle we are trying to mean an extremely small sub element. It could be a very small thing such as a grain of salt, a speckle of sand, or even worse, it could be molecules or atoms and whatnot. But unfortunately in the engineering context, particle does not mean something which is small. This is the first concept which I would like to emphasize to you people, that when we say in engineering particle kinematics as opposed to a physicist who says particle physics, that has a completely different connotation. Particle kinematics in the context of engineering means something else as opposed to particle, the usage of the word particles in the context of physics. So the root is quite different. When the physicists use this word particle, they usually mean atoms, molecules and whatnot, but the engineering route, which is the route that we will take, will mean something else, and I would like you to understand this crucial difference, and we are going to take this engineering route from here on, not the other one. So as I said, in engineering mechanics, atoms and particles are governed by is not what we are looking forward to. In fact, atoms and particles are going to be atoms and molecules in general will be governed by completely different set of rules which is beyond the ambit of engineering mechanics. In engineering mechanics, atoms and molecules is not the concern, but what we exactly mean by particles in the engineering context, I will come up to you in the next slide. So as we said, in engineering mechanics, that is the one which we are interested in, we encounter two terminologies, namely particle and body, and we are going to talk about particle mechanics at this point. So to define a particle or to characterize a particle, here is my simple definition of it. Particle is an object such that all points in the object have identical motion characteristics. Let me see illustrate what I mean. Let's take this object for example. This object, if it moves in this fashion, right, you could see my hand waving. So if this object is moving in this nice fashion, then all the points in this object, whether this one or this one or that one, all the particles have identical motion characteristics. Now that word motion characteristics is given in bold. What that means is that it has identical velocity at every point, it has identical acceleration at every point, it has identical displacement at every point in time. So this is a crucial distinguishing characteristics of what we call particle in engineering. I will give you better examples downstream in my slides, but at this point I wish that you take a note of this very important definition of what is a particle as opposed to what is a body. Again, these two words referred to in the very engineering context of its usage. So as I said, the motion characteristics, that word in bold that I have stressed, actually means the displacement, velocity and acceleration at each instant of time. So this is in opposition, this is in again sharp contrast to what we refer to as a body. So the same body this time, if it has a motion something of this kind, then as we will show through some of my animations which has already been posted to you, we will see that the motion characteristics is completely different for different points. It is not true that all points share the same motion characteristics. So therefore we have a crucial summary at this point, that there are two kinds of bodies that we encounter in engineering practice. One in which all points of the body share identical motion characteristics, and there is another kind of bodies which we encounter, the case wherein different points may have different motion characteristics. And let me elucidate these with more real life kind of examples. So here is a nice cartoon drawn by my student about an aeroplane flying. So definitely by the size of it you can understand that the aeroplane is by no stretch of imagination a small sized object, it is a fairly large sized object. So particle does not mean a small size object, but when the pilot does announce that we are flying at 900 kilometer per hour, every passenger here does have the same speed. If the aeroplane is flying at a constant speed, as I had demonstrated with this piece of duster, the same thing is happening in this aeroplane. In aeroplane there is a lady sitting in this window, there is a guy who is snoozing around, there is another guy here who is wide awake and looking below the window. But if there is a conversation happening between these people, every person will say that the speed with respect to the ground obviously is 900 kilometer per hour. So if the aeroplane is in fact flying in a nice smooth fashion without encountering any turbulence and the ride is very smooth, the crucial aspect is every point of the aeroplane, whether it's a living thing or whether it's a non-living thing like some point in the wing, some point in the tail, every point will have identical velocity. If the aeroplane accelerates, every point will have identical velocity. This will not be true if the aeroplane starts rolling in this fashion when it encounters turbulence and whatnot, or if it is maneuvering like a military aircraft, if it does some strange sorts of maneuver, then it is not true that all points have the same velocity. But here we are talking about this flight vehicle going in a straight path, going in a path of ascent. In whatever way you can think of this aeroplane flight, if you can think of a situation where all passengers experience the same motion characteristics. By motion characteristics I repeat, it is the displacement, velocity and acceleration. If all these motion characteristics are identical for each and every passengers occupying the seat of the aeroplane, as also each and every point in the plane itself, whether they are living points or non-living points, then we should be able to characterize this entire motion of a large aeroplane by any point, and mostly we will try to do it for the center of mass, but that's outside the purview of particle kinematics. The important point that I wish you take home is the following, that it is not necessary to discriminate between different points, because all points have the same motion characteristics. It is sufficient that we try and understand the motion characteristics of any point within this aeroplane. Any point, if we study the motion characteristics of any point, it will be true that all other points within this aeroplane will have the exactly the same motion characteristics. So therefore, the motion of this big aeroplane boils down to the study of motion characteristics of any one point of this big aeroplane, and that is why we call this as the motion characteristics of a particle, because we can simplify the problem at hand by, instead of looking to solve for the motion characteristics of each and every point, we simply look to solve for the motion characteristics of any point. And because we are interested in solving for the motion characteristics of any point, we are looking to call this as a particle mechanics or a particle kinematics problem, where there is a single point which is of our interest. So just to recapitulate what we talked about in the previous slide, as we have seen here, all points in the aeroplane, whether living or non-living, will have identical motion characteristic. That means that in the same interval of time, that is from takeoff to any other arbitrary point in time, all points will have identical velocity. During takeoff, the passengers, irrespective of the location where they are seated, will be experiencing the same kind of inertia forces. Again, that implies all points have identical acceleration. This is true if the passengers remain seated, and if they start dancing around in the plane like most crazy people do, then this is not true. But we are talking about the ideal case where all the passengers are nicely seated in their aeroplane, and the aeroplane is moving in a nice smooth fashion without encountering any crazy maneuvers or turbulence as such. So the last point is what makes this what allows us to idealize the motion of the aeroplane as that of a particle. So for determining the motion characteristics of the aeroplane, the study of the motion characteristics of any one point of this aeroplane is sufficient. The reason being that every point of the aeroplane finally shares the same motion characteristics. So whether you are interested in the point A or point B, it does not matter. So therefore, we will idealize this aeroplane to be a single point, and hence call this problem as a problem of particle kinematics rather than that of rigid body kinematics. So to give you a counter example, let us first look at an animation. I hope you are able to see the animation. This is what happens when you take your car for a wash in one of these garages. So in that roller coaster kind of arrangement, the car is lifted, and let us consider that the wheels are now spinning, but since they are not in contact with the ground, the car itself is not moving, right. Now consider the motion of each of these wheels. So each point, rather I should not use the word particle, each point in the wheel is going to have only a tangential motion, and the velocity of each point on this radius is going to be directed along the tangent. So that implies that the velocity at each point of this tire is not going to be constant in terms of its direction. Each point on this tire has different direction of its tangent, and therefore the velocity at each point is very different. The velocity at each point has different direction, even if the magnitude remains same. So this is again in sharp contrast. We were able to see whether you look in terms of magnitude or in terms of direction. But in this case of a wheel which is simply spinning about its axis without moving, that is, each point of this wheel is sharing completely different velocity characteristics. Maybe I can draw. So what I intend to tell you is the following. So let us say this is the wheel and this is the center of the wheel, and let us consider 2 points, one a circle and the other diamond. So at this instant of time, the circular point is having velocity directed along this tangent, and at the same instant of time this diamond point is having the velocity directed along the tangent. So at this point we can say, if I call this point A and this point as B, VA is not equals to VB, because as I see from the drawing, directions are definitely different. So that is why this case is not conforming to particle kinematics. This body cannot be approximated as that of a particle, because we have understood that particles are those particle idealization can be made only for those kind of objects where every point share the same motion characteristics. And we have brought out to you 2 examples. One, the case of an aeroplane which is flying on a straight path. This corresponds to a particle because every point of the aeroplane share the same motion characteristics, whereas that of a spinning wheel, there each point will have different motion characteristics and therefore it is not a particle. So please try to understand both the example as well as count. So just I'll run through what I have explained. So consider the wheels of an automobile. When the car is taken for a wash, the wheels will rotate freely without touching the ground, as you would have seen in the animation. So during this free rotation of the car wheels, all points on the same radial distance will have the same magnitude of velocity, but the velocity will be directed in the tangential direction, and since at each point the tangential direction will be different, therefore each point will have a different velocity, and therefore since each point is having a different velocity, this is not the case of a particle. So wheel is not a particle as we have mentioned. Okay, so this is a counter example. To complicate things a little more further, which is not just freely the wheel which is tied onto the car, but the car is not shown in the animation that you are seeing. This wheel which is basically rolling without slipping on a frictional surface. What does that mean? That means at the point of contact between the wheel, this is the wheel for you, and when this wheel is rotating, you will see that at this point the point of contact between the wheel and the ground always is subjected to a condition which is called the zero velocity condition. That makes sense, because when you say that there is adequate friction between the wheel and the ground, then the point of contact should not slip. That relative motion between the wheel and the ground is completely prevented because of the heavy friction that is there between the wheel and the ground. So at any instant of time, this red point will have a zero velocity, whereas at all other points you will have a non-zero velocity. In fact, a further analysis you can show that the velocities will again be along the tangent to this circle, but the direction of the tangent is again different. So herein you will find that the velocity is again different for different points on the wheel. So again we will be able to this time say that not only the direction but also the magnitude of velocity of all these different points on the rim of the wheel is going to be different. So again we have to conclude therefore that this rolling without slipping of a wheel again constitutes an example wherein not all the particles have got not all the points on the wheel have got identical motion characteristics. Different points in the wheel have different motion characteristics at each instant of time. So therefore, though the wheel is much smaller than the aeroplane can be idealized as a particle, whereas the wheel cannot be idealized of the particle. So the crucial take, please don't have a feeling that particle is something of a idealistic assumption and never occurs in reality. It is not so. It is just the way that you wish to analyze the kinematics of a given system. It may occur that a very large size object can be idealized as a particle, whereas even a small size object may not have the particle idealization. So the particle idealization has got actually nothing to do with the size of the object. The particle of idealization has got to do with the type of motion that you wish to analyze. If you are indeed sure that your aeroplane or your car is traveling on a straight path, there is no reason to think that it is not a particle. Similarly, even a small wheel, if it is undergoing only a motion wherein it is just moving in a translatory fashion, it is a particle. But if the wheel is actually rolling without slipping on a surface, or even if it is freely rotating about, then it is not a particle. So this distinction I think is very important, because you must understand when to apply the rules of particle kinematics and particle dynamics to a given problem, and when to not apply the rules of particle kinematics and particle dynamics to the problem at hand. So with this in mind, let us go forward. So as I said, the this is just these additional points is just what we have talked about in the last few minutes. Now coming back to this motion of a rigid body. So again you will keep hearing in the course of your engineering curriculum the usage of these two words, rigid body and deformable body. Again it is very crucial to understand the distinction between these two terminologies. A rigid body, which again is a sort of idealization, but let us try to understand how a rigid body differs with that of a deformable body. Again, if you think that the distance between any pair of points remains unchanged during the course of motion with of the body, then the body is said to be rigid. So again, to give you an example, as this body is moving, I don't think that if I draw 2 points here, one here and one here, okay. So I am drawing 2 points on this rigid body. As this body is moving, I don't think you will dispute with me that the distance between these 2 points that I have drawn is changing or not. It is not changing. So I can idealize the motion of this body, and if now I extend this argument to an aeroplane also, if I think about 2 points in the marked in an aeroplane, the distance between those 2 points is not going to change as the aeroplane is flying. The distance between 2 points drawn on the body of your car is not going to change because of the motion of your car, right. So in all these cases we are calling this as a rigid body. A rigid body is a body wherein the distance between any pair of points actually remains constant and does not change during the course of your analysis. So this is in contrast to a deformable body. If the distance actually changes, so if you have a spring like object, the spring like object within a spring, I can draw a spring for you. So let us say this is a spring. So under the application of forces, it is possible, under the application of forces, the distance between these 2 points will obviously change. So the distance between 2 points in a spring changes due to application of forces. Right. Similarly, if you consider an elastic bar, right, as you will see in your lab experiments in solid mechanics, once you apply equal and opposite forces on this elastic bar, this bar will be deformed, which means the distance between any 2 pair of points is not going to remain same, and that is when we will call this bar as an elastic bar. So in certain cases you will in fact be able to show or rather in fact you will be able to yourself convince that there will be situations where you will need to understand that the distance between 2 points in the body that you are analyzing is not going to remain fixed, and as such that will be the case of elastic body, whereas in the other case where the distance is fixed is going to be a rigid body. Okay, going ahead, in reality actually all bodies are elastic, as you will probably learn as you go through the engineering curriculum. In your strength of materials you will learn that in reality all bodies are elastic. But the important part is this, that for determining the bulk motion characteristics of the body it may be approximated to be the rigid body. So as I just demonstrated to you, the motion characteristics of this, while analyzing this motion characteristics, obviously the distance between any 2 points can be assumed to be remaining same. But I can obviously deform this body, I can apply a large amount of force on this body and actually crush it. When I in fact apply a large amount of force onto this body, I can make sure that these 2 points are actually coming close together. But in the cases that we are going to deal right now, we are not actually talking about such cases, we are only going to talk about the cases where we are talking about the bulk motion characteristics of this kind, and that is what is going to be of our interest in the next few hours. Yeah. And to continue my example with wheels, a hard pumped bicycle tire will approximate the rigid condition. As you can yourself feel that if your bicycle tire is pumped hard and when you press your bicycle tire, then you can see that it is very difficult to squeeze that bicycle tire tube, which means that the distance between the 2 points is very difficult to change. Whereas in the other extreme, when the air in your bicycle tire is going to has leaked out, then it is very easy to squeeze your bicycle tire, which means under that condition the bicycle tire is becoming more and more elastic. So again two example, one an example and one a counter example of a rigid body and what is not a rigid body or an elastic body. Again what we, to continue our example of aeroplanes, to determine the bulk motion characteristics of the aeroplane, it is not necessary that we consider that the aeroplane is made of steel or aluminum or any other alloy. It is going to remain just the same. But yes, if you are interested in solving for the vibration characteristics of the aeroplane wing, there the elasticity matters. But at present we are going to look for only the bulk motion characteristics and nothing else. Another thing that we must understand, and which is typically not sort of highlighted in an engineering mechanics book, is just like there are two kinds of bodies, rigid and elastic, there are two kinds of conditions which are imposed in this body. Either the body can be constrained, in which case it the effect of the body, so I'll again start writing in my notepad. So you have a body here, what the question is, under the action of certain forces, what should be the effect of the body due to certain forces. Now consider a body, the one that is lying closely in front of me, which is this one. If this body is not constrained at present, so at present it is not constrained, which means that if I am applying a certain force, it will keep moving. But now if I constrain this in this fashion, if I am applying a force, it is not moving. So what we are trying to analyze is an unconstrained body. Remember, the body can move only if it is not fixed. So this body, if it gets fixed at any place, then the action of this force can be resolved to a reaction force and the applied force. In this case there will be no bulk motion of this body. The body will move if only it is allowed to move. If the body is not allowed to move because you are clamping the body, then this motion is not permissible. So therefore I wanted to highlight to you this difference, since we are going to study the different motion characteristics of a body. The body will in fact move if and only if the body is allowed to move. If the body is not allowed to move, we call such kind of body as constrained body. And in a constrained body, such bulk motion characteristics is not possible. You can only have a vibrational or oscillating motion. Let us go through this line by line. The question that we ask at this point is, what is the effect of applied forces or torques acting on the body? So if the, as I just talked about, if the body is going to be constrained, then the effect of forces on this body is not going to cause any motion. If the force is that of a constant motion, then this force is going to only create what is known as static deformation. Probably you will see all the static deformation when you do a course in strength of materials. Whereas in an engineering mechanics problem, the body is unconstrained. That is, when the effect of the force is applied to a body which is allowed to move, then the body will in fact move. But in your strength of materials, you will see you will be solving beams which are cantilever or simply supported, and the effect of forces applied to such a simply supported beam or cantilever beam is not to cause the motion of that object, it is to cause static deformation and hence stresses and strains in such beams. But in engineering mechanics, as opposed to strength of materials, we are going to deal with bodies which are not constrained, and hence under the action of forces these bodies will undergo a bulk motion of the kind that I just showed you. So the last point is what is going to be our case for study, that is, effect of force on unconstrained body will cause the motion of unconstrained body, and that is what we are going to study in this course of a few hours now from now. Yeah, so engineering mechanics, and I see my spelling of engineering is wrong, I will try and correct it. So engineering mechanics is about particle dynamics and planar rigid body dynamics. I do not think in your course of engineering mechanics you are going to solve for spatial rigid body dynamics, that is done in a more advanced course in at an MTech level or so. So you are going to study throughout the course of in a semester probably entire particle dynamics and rigid body dynamics, which is planar rigid body dynamics. However, the part that I am going to teach you is only the particle kinematics part. So the present lecture content will be about the particle kinematics, and the objective of an engineering mechanics course would be to able to predict the motion characteristics under the action of forces. As engineers, this is a very crucial to understand that any component, that any engineering component will be under the action of forces. Now these components can either be constrained or be unconstrained. In case it is constrained, the effect of forces acting on these components will cause deformation, stress, strain, and if the stress strains are within acceptable limits, they will not fail, else it would. For the other extreme, when these bodies are unconstrained, the effect of forces will be to cause bulk motion of this body as dictated by Newton's second law. So you have to, as engineers, you have to predict what is the effect of force either on a constrained body or on an unconstrained body. So in an engineering mechanics course, our topic of interest is what is the effect of force on an unconstrained body, a body which is allowed to move. And for such bodies, as we just said, we are going to have a bulk motion characteristic. The body in totality is going to move, either it is going to move like an aeroplane or it is going to move like a freewheeling animation that we just saw. So it is very important for you to predict either kind of motions. So through engineering mechanics you are going to predict this kind of motions with given the forces. There is also a very nice converse problem. Suppose in the case of a satellite launch, we are looking to have a certain motion characteristics of a satellite. The ISRO people would want their launch vehicle to go in a specified fashion and to reach a particular point at a particular time. The converse problem therefore is also very interesting, that if you know that you have to go from one point to the other in a certain fashion, how will you apply the forces such that you in fact undertake that motion and nothing else, okay. So this is probably not in the purview of an engineering mechanics course, but none the same I wish to bring to your highlight, which is just the converse of the previous problem. In the forward problem, given the forces you are trying to predict the motion, in the backward problem, if you know that this is the desirable motion, or if you know as a reverse engineering problem that this is the observed motion, you can try and calculate what are the forces which have caused this motion. So both are very interesting problems in their own right, and hopefully we should try and eliminate them. Yeah, as I said, in these 5 hours or so, we are going to concentrate mostly on particle kinematics. I have eliminated to you what this particle idealization means. I will try and talk more about kinematics in due course. But the learning outcomes which I expect at the end of my part of the talk is the following. You should be actually by now you should be able to identify what is a particle and what is a rigid body motion characteristics. Any motion that you see, you should be able to identify whether this motion can be idealized as particle or that of rigid body. What I'll show you in the next hour of the talk is how to describe particle motion characteristics. By description, you could mean that either I can talk and talk and talk that this is how the particle moves, or the better idea for engineers is to stop talking and to show a graphical plot. So how to the description for engineers would mostly be in terms of a graphical plotting, which essentially gives the idea that this is, or more importantly carries the information that this is how particle is moving. And again, in contrast to what is usually not given in a book, we will spend a lot of time in trying to visualize the motion, and we will presently concentrate with motion under known acceleration. The other things will become more complicated. So in the next 4 hours or so, I will show you a number of animations, and these animations have also been uploaded in your course pack so that you can refer to them as and when you want. It is very important for you to gain proficiency in the visualization of motion. If you can visualize in your mind how the motion is taking place, then the mathematics and the analytics is just a child's play for you. So even I would suggest that you would practice to make these animations yourself such that you get proficiency in visualizing the motion characteristics in different kinds of problems. So with this introduction, I think we will make a more formal beginning, and just like we elucidated to you the meaning of particle, in this slide I would like to elucidate to you the meaning of the word kinematics. The word kinematics, though it sounds heavy, it is actually a very simple concept. We have to describe the motion characteristics. Now you may say, what do I mean by describing? Can I describe someone? Now by description, what a naive idea, a simplistic idea could be that, let us say my body of interest is a train this time as opposed to a plane in the first slide. So a description of the motion characteristics of a train, let us say the Mumbai Delhi Rajdhani Express, could be just its timetable. It leaves Bandra Central at 4 o'clock in the evening, it reaches Surat at 8 o'clock in the night, it goes to Delhi at probably 12 in the noon. So that is the description of motion characteristics, but that is a layman's description, that is not a description that is desirable from an engineer, because what is it that it lacks? It lacks the description, this description that I have just given you in terms of its timetable lacks the information that what happens between two stations. You have said that, well, it leaves Bandra at 4 o'clock in the evening, if I am not wrong, and reaches Surat at 8 o'clock in the night, but what happens between Bandra to Surat is not known in the timetable information. Whether the train runs fast, whether the train runs dead slow, whether the train is accelerating, whether the train is decelerating, nothing is known about it. So therefore such a naive description is not suitable for the engineering purposes. We want a description which is more complete. So given any 2 points, whether it is in time or on the any 2 points on the train track, we should be able to completely describe its motion characteristics. And what do I mean by motion characteristics? 3 things: displacement, velocity, acceleration. Any time you tell me what happens at 8:15 in the night, I should be able from the description I should be able to tell you that yes, this is at 8:15, it is at such and such place, or it is moving at such and such velocity, or it is moving with such and such acceleration. So the description should be complete in this regard, that throughout its period of travel you should be able to completely describe the location of the train, you should be completely able to describe the velocity of the train, you should be able to describe the acceleration of the train. If these three characteristics can be determined for any time during this period of motion of the train from Mumbai to Delhi, then we will say that the description is as complete as it could get. And we will try and determine such description, though not for the Mumbai Delhi Rajdhani Express, but equally complicated problems or perhaps more complicated problems. So the scientific description that we are looking at is such that it would enable us to determine its location at any point of time during its travel. What we are looking forward to is that at any time we should be able to describe its location, not only its location, its velocity, its acceleration also should be determined from such description. Well, these days in wherein you have apps and you have a GPS tracker, you could say that the complete description is actually obtained on, let us say, a Google map, wherein with a pointer you can these days even taxi drivers have such app, wherein with a pointer they can determine its location. That description is complete, definitely true, but even from such a GPS location you cannot determine velocities and acceleration, you can at the most determine positions. So we want a description which not only gives position but also gives velocity and acceleration. So as I just said, that these app based taxi drivers will use a mobile device where at every instant of time the position is accurately determined on a map. But even with that sort of a technique, it is possible, I would not say it is impossible, but it is quite difficult to determine the velocity and acceleration characteristics. Again this therefore we will not take that to be our best example of a complete description of motion characteristics. What we will call as a complete description of motion characteristics is going to be our objective in the next few hours or so, and let us see if I can convince you that a description in a mathematical form, or better still in a graphical form, actually attains this objective. Okay, so to summarize this slide, therefore I hope at this stage you understand what I mean by kinematics. Kinematics is the description of motion characteristics, and by description what we desire is the following: we wish to have complete information regarding the location, regarding the position, regarding the velocity and acceleration of this body. And remember, as we are talking about particles, therefore when you, even if it is an extended body such as an aeroplane, all points within the body will share completely identical motion characteristics. So therefore it is sufficient to look at just one point of the body and determine its motion characteristics. Whatever motion characteristics you determine for a certain point will be true for every other point. Yeah, so the objective of kinematic analysis will be to determine a mathematical function to determine the position of the particle at every time instant. And it will be shown to you that once you determine a mathematical function which gives the position at every instant of time, the velocity and acceleration can be determined from such mathematical function. So therefore we will in fact have a complete description of motion characteristics once a mathematical function for position against time is obtained. So that is the purpose, as I will go I will elucidate to you. So the kinematics is therefore the study of the geometric character of the motion, namely position, velocity and acceleration, which is what I have been emphasizing again and again. And what I will try and convince you through the course of these next few hours is that a graphical presentation of such motion characteristics is actually very informative. All the information that is carried by the formula can be very nicely represented in graph, and the best thing is that you can plot your graph, such a graph, using just a simple piece of software such as MS Excel, or better still MATLAB or Mathematica or whatever. So we will have some exercises for you wherein you will actually plot these graphs given the functions, and also the reverse, given the graphs determine the functions. But either way, it's going to be a very interesting study. The part that is not in the purview of kinematics is the forces. We will actually not link the forces with this motion characteristics. Kinematics is the study of motion in the absence of forces, but the kinematics will get linked to the forces in the next part of the course, which is called kinetics, and together they form the subject matter of dynamics. So in kinematics we are not going to talk of any forces which are causing this motion. In kinematics we are only going to say that we wish to describe the motion characteristics either through a formula or through a graph, right. But once the formula is determined for position, how to determine the additional information regarding velocity, acceleration and whatever is what the next few hours we are going to deal with. Okay, so as I just said that it's not a child's play for dealing with kinematics of particle. So here you see that the position time characteristics of a launch vehicle is continuously tracked. So the as I said, kinematics is about a description of the motion characteristics of the body of your interest. Let us say we are interested in the launch vehicle, like ISRO scientists are, they are interested to determine the position time characteristics of a launch vehicle. So what does that mean? They are continuously plotting where the launch vehicle is in time, with every time how far it has gone. So the displacement could be from the point of the launching site to where it has gone, that needs to be continuously tracked. So this is a graphical representation, and this is what the ISRO scientist will definitely do during the time of its launch. They will continuously track with the trajectory of the launch vehicle. So this sort of an information is what we are looking at, and it will be shown to you, it will be taught to you that from this displacement time characteristics, how can you recover additional information like velocity and acceleration if you want to. And this is very important, at least for the satellite application that we are talking of, because the success or failure of putting the satellite at the desired location depends on this motion characteristics. As you observe this plot, you should be able to predict whether actually the launch will be successful or a failure. So determining this sort of plot, whether through just a video imaging or through a mathematical function, is extremely crucial for this sort of an application, and this is just an example. In very many different cases, this plot is going to be playing a very crucial role in many downstream applications. Okay, before we move further, I will throw myself open to any questions at this point, because now we are getting into the heart of the subject. If you have any questions, please shoot them. I'll take a 5 minutes pause to take your questions at this point. Yeah, PhD has asked me a question. What is the difference between kinetics and dynamics? Actually, dynamics is the subject of dynamics has two parts: kinematics and kinetics. So kinematics is the study of geometry of motion, where you don't pay any attention to the forces which have caused this motion. Okay, that's the part that we are going to cover in the present module of 5 lectures. So kinematics is about the description of motion. Relating the motion to the forces is the kinetics, and kinematics and kinetics together comprise dynamics. I hope that answer is clarified. PhD, could you please respond with a yes or no? Yeah, KSR, you wanted to ask some questions?
Sir, I have one doubt.
Yeah, please.
Rotating wheel.
Sorry?
The wheel is sliding. If the wheel is sitting without slipping.
Okay.
How
Okay.
Can we assume that? How can we assume that motion? Whether it is not a particle or it is assumed as a particle.
No, see, I got your question. Let me repeat your question. So I showed the example of rolling without slipping of a wheel. You are saying that if the wheel rolls with slipping, whether it's a particle or whether it is a body, right? Have I understood your question
No, sir.
correctly?
I am. My question is not that, sir. It is not
Okay.
at all rotating. It is sliding. Without rotating, it
Okay.
simply slides.
Yeah, if it is only sliding, okay, now I've got your point. The wheel is not rotating, it is simply sliding like this, it is sliding, okay. If it is sliding, can it be a particle or can it be a body? It's a very interesting question. Let's argue let's argue this thing out. If it is sliding, that means does all particle of the wheel have the same motion characteristics or not? So let's take something like a wheel. Let's take this piece of chalk, if you can see, as a wheel. So this wheel is just sliding in this fashion, right? Now please tell me whether all particles have same motion or not in this experiment that I am doing. The wheel is just sliding on this
All
table.
are in same.
All are having identical motion
All are
characteristics
in.
if it is sliding. So therefore I need not look at individual points of this body, rather I can concentrate on any arbitrary point because I have determined that all points are having the same motion characteristics, and therefore in this case it's a particle. It is not a body, because this case is a very special case where all points in the body is having identical motion characteristics. Therefore this
What?
complete sliding without rolling of a wheel is that of a this idealization can be construed as a particle idealization for the wheel. Yes, I was stopping you. You have something else to say?
No, sir. Center of the wheel. I am asking you about the center of the wheel. Center of rotation is zero velocity.
No, center of rotation now will not be zero velocity because you're saying that the wheel is sliding. If it is sliding,
Linear
then
velocity.
all points are undergoing a translatory motion in this fashion, right? All points are undergoing translatory motion, including the center of the wheel, which is having a translatory motion.
Motion. It has only translatory motion.
Yes,
Center of the
because
wheel.
it is sliding, there is no rolling. As you said, rolling is zero. There is no sliding. Everything is a translatory motion, and therefore it is a particle.
You have answered my question, sir. Yes, sir.
Okay, thank you,
Understand.
thank you,
Understand.
thank you. One more question, please. Any? We have time for one more question before we again begin the formal lecture. PECTN is asking difference between a constrained and an unconstrained body. I thought I just explained to you that a constrained body is that in which there is certain restrictions that the body cannot move. A portion of the body is constrained to stay put at a particular point. That's a constrained body. Whereas in an unconstrained body, you don't have such restriction. So again, to give you an example, if you have a cantilever beam, then in a cantilever beam, the cantilever end is obviously having the restriction that that point cannot move. So even if you apply a force to the cantilever beam, it can deflect, but it cannot move. So such cantilever beam study will not be a part of engineering mechanics or dynamics. Rather, it will be a part of strength of materials, where you will actually study deflection. Whereas for the same cantilever beam, if you now relax the cantilever conditions, if you take away the cantilever conditions, then this beam is actually free to move. Now if you apply a force to this body, it can move following the Newton's second law of motion, which is F equals to ma. So the acceleration in response to a force will be F by m, right? So all that I was saying is that the action of a force on a body such as a cantilever beam will be different whether or not you have a constraint. If you in fact have the cantilever constraint, then the body will not move, whether if with an acceleration F by m or otherwise. But if that cantilever condition or the constraint condition is relaxed, then the body will move following simple Newton's laws of motion. I hope PECATN finds this answer satisfactory. Okay, we will now continue with the formal lecture. Others can please type in as to how you are feeling this lecture is going, and accordingly we can take some course correction if need be. So we will now get into little more formalisms, mathematical formalisms. Yeah. So any analysis will begin with a proper choice of coordinate system, and at this point we will try and elucidate what are the different kinds of appropriate coordinate systems that will be used in practice. Yeah. At this point we will elucidate what are the different appropriate choices of coordinate system for different kinds of problems that we encounter in engineering mechanics. So the reason that we need a coordinate system is the following: the position of the particle will be described with reference to the coordinate system. To describe the position of the particle, you have to choose a coordinate system, and the choice of coordinate system will be arbitrary, as we will see that you can choose a Cartesian coordinate system, you can choose a cylindrical coordinate system, you can choose a Cartesian coordinate system at different origins, right. So there is nothing like the choice of coordinate system. Every analyst has his own free will to choose the coordinate system, as we will show in different choices. But a smart analyst will be smart in his or her choice of coordinate system. So the choice of coordinate system should in fact be dictated by the type of problem that you are solving, and this is what I will try and exemplify with different examples that I have lined up for you. So let us again go back to animation. Okay, so this is an animation wherein we are showing two vehicles which are running on a straight highway. There is no lane crossing, there is no overtaking that is possible. This is a very idealistic situation. We are not addressing all these things. So there is a green car and a yellow truck, as you can see they are moving nicely in this straight highway. Now as we have defined our objective in kinematics, we should be able to track the functional relation with time for the position of either the yellow truck or the green car. So both the yellow truck and the green car, the position of these car and truck has to be determined as a function of time. Now to determine the position, you obviously need a choice of coordinate system. You could put a coordinate system here, you could put a coordinate system here, you could put a coordinate system anywhere else. But before trying to fix the coordinate system, let us try and analyze in this case what is the description that we are looking at. Now as I have just said that in this case I am disallowing any overtaking or lane crossing. So forever this yellow truck has to move along this straight line, forever this green car has to move along this straight line. So obviously their y position is not going to change. So there is no fun in choosing actually an x and y axis as has been shown in this animation. All that we actually wish to determine is the position x, but the position x is to be determined from where? Should it be from this point, or should it be from that point, or should it be from this point, or should it be from this point? So that choice is perfectly arbitrary. There is no reason that I will tell you that always you should choose the coordinate the position of the truck from this point. Similarly, there is no reason that someone else should tell you that you should always choose x from this point. You are living in a free country and you are perfectly free to choose the coordinate system anywhere you want. So therefore the point is this, that for this problem, from the nature of the problem, it is very clear that we wish to choose a one dimensional coordinate system in this problem. Only x is desirable. There is no y component which is desirable in this problem. It is a redundant information if you choose an x and y system or even a z system. But you have complete freedom to choose the origin x equals to 0. The origin x equals to 0 may be here, 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 or maybe even outside this animation. It may be somewhere here which is not even shown. Okay. So you have complete freedom as far as the choice of origin of coordinate system goes. In fact, you are free to even use a redundant coordinate system wherein you account for y and z information, but that coordinate system is redundant and it is a stupid idea in fact to choose a three-dimensional coordinate system to describe this problem, because here you know for always y and z is going to remain fixed. So why bother to choose such a coordinate system? The smart choice obviously is to have only a one dimensional coordinate system involving only x and nothing else. Okay, going back, so that was the animation of for rectilinear. So this kind of motion, as I have just shown you, the example of which is motion of a vehicle in a straight highway is referred to as rectilinear motion. And to give you a more technical definition, which is going to come up as I am looking through. So the assumption in this example was that lane crossing is disallowed, and as I just talked through, one variable was adequate to describe the motion of the vehicle, just one variable, which is x, but the origin of the coordinate system may be chosen arbitrarily. There is nothing like this is the choice and you have to follow it, anything is perfect. But remember, despite the fact that the position will depend upon the origin of the coordinate system, the position of the vehicle will be defined, but the distance between two time instants, the displacement of the vehicle between any two time instants does not depend on the choice of coordinate system. So what I am trying to say is, let us say this is my car, and as I have talked to you, this is my choice of coordinate systems x. So let us say this is the position at time t equals to 0, and this is the position at time t equals to capital T, right. So therefore this is the distance, so I will call this position as x0 and I will call this position as xt. Let us say someone else is analyzing, that person is also smart enough to realize that there is only one coordinate system that is required, there is only a one dimensional coordinate system that is required to describe the motion characteristics for this problem, but he chooses the coordinate system, I call that x prime, the origin of which is here instead of here, okay. The origin of this analysis, of his analysis coordinate systems, is at a different place. He is also using a one dimensional coordinate system, a smart guy. He knows that there is no point in using a two dimensional coordinate system involving y and x together. So this, the value that he reports at t equals to 0 is x prime 0, and the value that he reports at time t is x prime t. Now obviously x0 is not equal to x prime 0 because the two origins are not the same, right. Similarly xt is not equal to x prime t, right. However, the distance between these two time intervals, which I call it as s, that s in the first coordinate system is xt minus x0, and the distance s calculated by the second analyst, and I will put a prime just to denote the fact that this is as calculated by the second analyst. This s prime is x prime t minus x prime 0. Though xt and xt prime is not the same, though x0 and x0 prime is not the same, it is so from the geometry it is clear that s prime is equal to s, and that is very crucial. So that is what I meant by saying that though the position as given by every analyst will depend upon the choice of the origin of the coordinate system, but the distance that is covered between two arbitrary time points is actually independent of the choice of coordinate system. So that's the remark that I had given in the slide, and I will write that once more. So the distance covered between two time instants is independent of choice of origin, okay. So this will come in handy as we will try to find the velocity, okay. So the origin was chosen arbitrarily, the position definitely is with reference to the choice of coordinate system, different choice of coordinate system will lead to different positions of the vehicles being determined in the different coordinate system. But this is crucial that the displacement of the vehicle between any two time instants do not depend on the choice of coordinate system. Wherever you choose your coordinate system, as far as you are trying to analyze the distance between 2 points in time, it will not be subjected to this subjectivity as to where should you put this origin, and this is what we call rectilinear motion. So let us, so after giving you the example, let us now try to generalize and find out the general characteristics of this kind of motion, which we will call as rectilinear motion. So rectilinear motion, firstly, the stark distinguishing characteristic is that it is always happening in a straight path. Okay, so motion of the body, which is now idealized as a particle, is going to happen only along straight path for rectilinear motion, and the position can be described by using only one variable, namely x. There is no point in a description where you have the motion in terms of x and y and z and whatnot. There is no reason to choose a two-dimensional or three-dimensional coordinate system in the description of rectilinear motion. Now another interesting characteristics for which I will return to, as you see this animation, not only is the position along one direction, the velocity is also along this direction. There is only one direction that is of interest. The position, velocity, acceleration, all are having the same direction for all times. This is really a very marvelous idealization. As we will see, this rarely occurs, but still it is not too far-fetched to think that within some time intervals in some expressways and highways, you will see that this is the sort of motion characteristics that does take place. So in this case, definitely it is rectilinear motion. As this may be a tourist bus, and if you realize, and such tourist buses do in fact go straight without overtaking and so and so. So the important factor is this, that as long as it is moving in the straight highway, the velocity magnitude can change, but the direction of velocity is always going to be along this, because there is no way it can change its velocity. Lane crossing is disallowed, right, and people do abide by such rules. Then we have a case of rectilinear motion. Similarly, acceleration also, there is, since the velocity always remains in this direction, even though the magnitude of velocity changes, the magnitude of acceleration also changes, but the direction of acceleration or velocity always remains same. So therefore, a very crucial remark at this stage is that not only the displacement but also the velocity and acceleration are all directed along one direction during this investigation. So it is rectilinear motion if and only if displacement, velocity, acceleration are all along one line for the entire period of analysis. As we have brought out through this example, that there is absolutely no need for going for any analysis wherein you incorporate two-dimensional or three-dimensional coordinate system. One-dimensional coordinate system, and we will call that as x, is adequate for the representation of such motion. All we want is firstly to determine a function of position with time. If we are able to determine a function of position with time, velocity and accelerations will be determined. But before going that far, intuitively we are very clear that all these things, all these motion characteristics, call it displacement, velocity or acceleration, will be along one direction, and that is the signature characteristics of rectilinear motion. As we elucidated and emphasized, the choice of origins of the coordinate system can vary between your observers and between the analyst. Every analyst can choose different choice of origin system, but as we have just seen, though this choice of origin will affect the numerical values of the position that he or she reports, but it will not affect the distance between two fixed time instants, and that is all that we need in determining velocity and acceleration for downstream calculation. So even though there is liberty in the choice of origin, even though the positions will be different as reported by different observers for the different choices of origin, the velocities and accelerations will in fact turn out to be just about the same. and we will do some of these calculations as we go through. So accordingly, the physical interpretation of the coordinate as the distance from the origin varies between observer. The position will vary, but displacement between two time instants is independent of the choice of origin, as I have just written down in the one note also. Okay, now let us complicate life a little more, that instead of rectilinear motion we are now looking at planar motion, a motion wherein the vehicle can move within a plane. Though this animation suggests that it is moving through some hills, we are saying that it is not actually ascending over the hill. The height of the hill is this pathway is at the same height. But now if you have to describe the motion of this car as it goes through this track which is at the same height, you have to necessarily use two variables, one for x and the other for y. If I have to determine the position of this car, I cannot describe it possibly with only one variable. It is quite non-intuitive to think that you will be able to do so, but and this time lane crossing is also allowed. So therefore, there is no way in which I can describe this car motion with only one variable. I need two of them, one to describe that how much left or right it is from a choice of origin, and how much top or bottom it is from a choice of origin. But again here the same question arises that the origin can be at different places, okay. And a better example that we have concocted is that of a motion of a carom, and I think we have an animation. Yeah, so here you see as you play caroms in your hostels, this is the red coin which is moving through. Now as you see, to describe this motion, you cannot describe the motion of this red coin with a single variable x, because the motion of this coin is such that it is moving leftwards, it is also moving from top to bottom. So this if this is the particle of your interest, and again we call this as a particle described despite it being a body of reasonably large size, maybe half an inch or so, it is having identical motion characteristics at each point, and therefore we call it as particle. All that we need to understand is that the motion of any one point, and that is sufficient. That was just a repetition, but at this stage, in contrast to rectilinear motion, this is not a rectilinear motion. Why? Because firstly, to describe the motion characteristics of this carom coin, we need two variables as opposed to a single variable required in rectilinear motion. And why is it that we cannot describe it with one variable? Because it has both motion from left to right as well as motion from bottom to top, and after hitting this edge it comes from bottom to it travels in the negative y direction. So therefore, it is more appropriate to choose an xy coordinate system for the description of motion. So to describe the motion characteristics of this carom ball, we wish to find x of t and y of t. Both x of t and y of t need to be determined. You cannot just say that I will determine only x of t. If the carom ball was moving only in this direction, then you can say it is x of t and only. But since the carom ball is having a motion of this kind, to describe its motion within this entire period of the game, you need both x of t as well as y of t. So therefore, the first takeaway is that this motion of this red coin is not describable through a rectilinear motion characteristics. This should be necessarily planar motion, and at the very same time we realize for planar motion we need, for description of planar motion we need two variables at least, namely in this case what seems very appropriate at this stage is the choice of x and y. But again, similar to rectilinear motion, we find that there is absolutely nothing binding us to choose this coordinate system with origin here. We could choose a coordinate system with origin here, we could choose a coordinate system with origin here, or anywhere else you want to. It can be even outside the carom board. There is no need that it has to be this. This argument is just similar to the rectilinear motion argument, that the choice of origin of the coordinate system is left to the individual analyst. But as we will see that despite this freedom given to the analyst, the velocity and acceleration characteristics reported between different analyses will not change. So I hope you get the point as what is the difference between rectilinear motion and planar motion through these two examples. Important point is, to describe the motion characteristics we need two coordinates in planar motion as opposed to rectilinear motion. Now in the Karam case we have seen that the xy is the obvious choice, but we will bring out more examples more with varying level of difficulty, wherein we will see that probably not the xy system but maybe an r theta system is better. So even it could be a non-Cartesian system, but at this stage I would not like to complicate that far. I would simply like to state that two coordinates are necessary for description of planar motion, and by similar analogy we will do spatial motion also, where we will see three variables are required for a complete description of motion. So as we said, for the Karam striker we need to describe the motion with two variables, and what seems to be appropriate is the xy system. And here we have just taken a example where the carom board is of size 10, maybe you can call it 10 inch. So for a 10 inch by 10 inch carom board, we have just elucidated an example where the origin is selected here, and with this as the origin we are trying to find out the x as a function of time, the y as a function of time of this red coin, and that will serve as a kinematic description, or what we keep shouting as motion characteristics. And we will show you how to get the velocity and accelerations once x against t and y against t are both determined. And as we have seen that the origin of the Cartesian coordinates is arbitrary, not only the origin, even the orientation could be arbitrary. There is no reason that these coordinate systems have to be aligned in the fashion of left to right and top to bottom. It could be aligned in it could be oriented in an angular fashion also, but I'd leave that complication at this stage. At this stage I will think that okay, the origin can be changing, but with a little bit of thought you should be able to convince yourself that it is possible to choose a coordinate system with a different orientation also and still describe the motion characteristics of the carom ball. Okay, let us take a different example now, where I would probably like to think that Cartesian coordinates is not the right choice. Okay, so let us talk about a car which is turning on a circular track. So this is a car, it is turning on a circular track. Now you may say that obviously this is a planar motion problem, because to describe the position of the car you need two coordinates x and y. The position of the car can be described in terms of x and y. But the point is, this x and y variable are always going to be related through this equation, which is x square plus y square equals to r square. Just I will elucidate once again through some notes. So what we are saying is that, let us say this is a circular track and we have our origin somewhere here. So to describe the motion of the car, which is sometimes here, with sometimes here and sometimes here, you could say that always I will look to report the value of x comma y. So this is x0 comma y0, this is x1 comma y1, this is x2 comma y2. Okay, there is nothing wrong actually with this description, where you are trying to describe the motion of the car as it is going on a circular track through two variables x0, x and y, where x and y could be centered at the origin if you want. This is x and y coordinate system, and to describe the position of the car, so to describe the position of the car, x comma y may be reported at every time, for every time. But then a smart analyst will be able to realize that reporting x and y is actually redundant. If you report x, y is obvious, because at each instant of time you have, so to say, this equation to be satisfied. So at each t you must have x square plus y square equals to r square. So even if I give x0, x1 and x2, you should be able to recover y1, y0, y1 and y2 through this relation. So therefore, using an xy system in this case, though it appears to be a planar motion, using an xy system for this case is actually not the best choice. The best choice is a choice which which allows you to describe this problem with the least number of variables. Why unnecessarily make life complicated by introducing two symbols x and y when you know that there is no need for describing it through two symbols, because the two symbols, the two variables are interrelated, x and y. So we will try to get some simplification by actually trying to eliminate one of these variables, which is what precisely a cylindrical coordinate system will let us do. But at this point I wish to emphasize this fact that though this is a planar motion, this planar motion is not well suited to a description of, in terms of Cartesian coordinates x and y. The better choice would be to describe through this angular variable theta. So instead of describing the problem through x and y, I might as well choose to describe this problem. So this is the circular track. Instead of describing x and y against time, I might choose to describe theta against time, where theta is measured in this fashion. So a better description of motion which avoids any redundancy is theta against time. Let me repeat my argument once again. This was the case of a car moving on a circular track. Now obviously one might think that to describe the motion of the car moving in this circular track, it is not proper that you describe it in terms of one variable x. You would like to describe it in terms of two variables x and y. So to describe this motion, that analysts with a simplistic viewpoint thinks that it could be represented as x against t and y against t, two functions he wishes to derive. But then a sharp fellow comes in and says, why are you describing in terms of two variables? Because if you describe one of them x, then the other variable is automatically determinable, because at each instant x square plus y square has to be equal to r square. So therefore there is no need to do an analysis only for x. So therefore there is no need to do an analysis, I am sorry, for both x and y. So the better and a smarter choice in this case would be to describe the motion characteristics in terms of this theta variable. So at each instant of time, if we look to describe the motion characteristics in terms of theta, then definitely the motion characteristics is going to be completely derivable, and there is no redundancy in this formulation, because at every instant of time you need to specify a position that will in fact come through theta t. But please note, this is not going to be rectilinear motion. If you think since it is describable by one variable, it is therefore a rectilinear motion. No, it is not rectilinear motion. The reason being that for description of rectilinear motion, you must understand that the velocity and acceleration are all along the same direction. But in this case, as we know that there will be a centripetal acceleration which will not be along the direction of the theta. So the theta direction at each point will be like tangent. The unit vector in the theta direction is this. Okay. So as you will see in details, the velocity will always be along the theta direction, but the acceleration will not necessarily be along the theta direction. So as will be shown in this case in details, will be shown acceleration is not necessarily along E theta, and therefore this is not rectilinear motion, though it is describable by one variable. Despite it being described now by one variable, it is not a rectilinear motion simply because it is describable by it is not a rectilinear motion simply because acceleration does not always point towards the same direction. In fact, velocity always changes direction because E theta itself is changing direction, right. That's a subtle argument, but we'll bring forth that in a due course. At present, I hope I am able to convince you that despite this kinematic description being possible with the choice of only one variable, it is not adequately it is not satisfying all the characteristics of rectilinear motion simply because the acceleration is not always along the same direction. Okay. So, with that, let us return to the lecture material. So, this is the question that I had left open in the presentation slide. So, is this motion rectilinear or planar? Despite being describable by a single variable theta, it is not rectilinear, it remains planar, but it is just that even planar motion can be represented by a single variable. It is not required that planar motion have to be represented by two variables, that is not a requirement. As you have seen in this case, the a planar motion can be represented by one variable, but it is just that for description of this velocity and acceleration, you require two directions. You can't do it with one direction as we have just shown you. So, velocity at any instant is along E theta and acceleration is not along E theta, that is the argument which I have just given. So, these formal proofs of this we will do it in due course as we go along. Okay. Now, let us take a general motion of a car that is traveling in this nice curvy path. So, instead of looking for a path which is circular, this path could be any arbitrary shape, it could be it need not be circular, but it is definitely curvilinear. So, instead, just to extend that argument of car moving to a circular track, now we are taking the car moving along a general track, but with the same height. So, again we can say the position of the car can be described in Cartesian coordinates as xy, this can be done, in which case it is obviously understood that it is a general planar motion. But then, as hopefully by the end of this course you will understand that a more appropriate coordinate system is not the xy global coordinate system, but a coordinate system along the direction of this curve. That may sound a little bit non-intuitive, but hopefully we will be able to show that to you. So, what we mean is that you could put a coordinate system along the track of this car, just like we have put a coordinate system on the circular track for you. Yeah. So, this is the coordinate system along the circular track. Similarly, and this was easy to visualize because this is circular. So, at each point you know what is the tangent, and you put this cylindrical coordinate system is basically such that at each point this tangent is your vector of interest. Now, coming back to this general case, here you could put a coordinate system, not necessarily the xy coordinate system here, but work with a coordinate system which is S, which I call it as a S coordinate system or a path coordinate system along this circular path. So, at each instant of time the tangent to the circular path is the S, and then you pick up another coordinate system which is perpendicular to the S and directed towards its center of curvature, and that is called N. But anyway, we will keep at this point I do not wish to get into much rigorous details of this presentation of this problem, but all that I wish to emphasize to you is that even in a planar problem, it is not necessarily, as in the case of carom board problem, it was quite obvious that you need a coordinate system which has x and y, because finally the carom board moves like this. We said that fine, the orientation of this coordinate system is left free for the choice of the analyst. Similarly, the origin of the coordinate system is left free from the choice of the analyst's perspective, but that is not the only choice. That is the point that I wish to drive home. For the case of circular motion of the car as well as the case of general motion of the car along a curvilinear track, it is possible to describe the position of the car along this path by simply saying that what is the distance that the car has covered along this path. Okay. So, let us say the driver over here has said that as he is driving from this national highway 1, he has covered 100 kilometers. So, that means on this curvilinear track, if I take a tape and measure 100 kilometer, I should be able to determine his position. That is a completely fair description of position. You may feel that the description of position is coming through by the use of just single variable, and therefore it is a rectilinear motion. No, it is not rectilinear motion, because at each instant of time the direction of velocity and the direction of acceleration is changing, which is not allowed for rectilinear motion. So, there will be problems in disguise where you can mix up between what is a rectilinear motion and what is a curvilinear motion and what is a planar motion in Cartesian coordinates. Please get these ideas straightened out before we jump into actual problem solving. So, that is why in these introductory sessions I wanted to clarify to you the basic concepts which lies at the foundation of problem solving, rather than throw open the problems to you. As I said, the approach that I like to follow is to first gain a clear understanding of the theory, and once the theory is clear, problem solution should not be difficult, and therefore I do not really believe in solving lots of problems. I believe in solving few but very nice and difficult problems that should set ourselves up for the for our learning. Okay. So, now instead of introduction, we will actually begin our study of the simplest type of motion, which is rectilinear motion, and by now you know the terminologies, what is a rectilinear motion, and therefore we are all set for the description. So, we are now going to analyze the rectilinear motion. So, as we said, the simplest example of a rectilinear motion is that of a motion of a car which is along a straight line or a highway, and lane crossing is disallowed. So, as we argued at length, the position of the car can be best described with reference to a one dimensional coordinate system, and obviously it is going to be a Cartesian. For one dimensional, there is absolutely no ambiguity. There is nothing like cylindrical one dimensional system or spherical one dimensional system. If it is one dimensional system, the only possible choice is obviously Cartesian. So, this Cartesian with a question is just left to confuse you. It has to be Cartesian, it cannot be anything else. But the only issue is that the origin can be selected arbitrarily. Whatever be the choice, origin can keep shifting. Sorry, whatever be the choice of analyst, the origin can shift between the two analysts. So, at any time xt will denote the position of the particle, which is the displacement with reference to the origin. Now, between two times t1 and t2, particle is at x1, which is x at t1 and x2 at t2. So, this is the relationship between displacement and time, and either it can be a mathematical function or a graphical plot, and we will try and emphasize both to you, how to recover a graphical plot out of a mathematical function and how to determine a mathematical function intuitively from a graphical plot. So, what we mean to say is, let us say xt is 5t, right. So, I hope you know how to plot functions such as this in Microsoft Excel, and it is better still if you are exposed to some scientific computation software such as MATLAB or maybe Mathematica or anything else. But I think to make your learning a little more active, instead of just looking at books and trying to mug up some of these figures, you should start plotting these figures. So, to start with, here is a simple plot, xt equals to 5t. So, if you have to do it in Excel, you should just simply have an array of numbers t, let us say starting from 0 to 10 in steps of 0.1 or something, and in the neighboring column you just have to write the formula 5 times the column value adjacent. Let us say the A column is T, the B column you have to write the formula 5 times A1, 5 times A2, 5 times A3 and so on and so forth. You will get a array of numbers in the column A, adjacent to it an array of numbers in column B, and then using the obvious syntaxes you should be able to generate a plot between the A values and the B values, and that plot should look something like this. So here as we said, for rectilinear motion our objective is to determine a functional relationship between the position variable of the body of interest and time, and this is going to be just x of t. Just to start with, I have taken an example where this position changes with time in this fashion. What does that mean? At time t equals to 1, let us say the object is 5 meters away. At time t equals to 2 seconds, the object is 10 meters away. At time 3 seconds, the object is 15 meters away, and so on and so forth. So this function exactly captures position with respect to time, which our timetable of Mumbai Rajdhani Express was not able to capture. So at given this, if this is indeed how Mumbai Delhi Rajdhani Express goes, then you can tell, looking at this formula, that what is the position of the train at any time since it has left Mumbai, right? And similarly velocity and acceleration. But at this point let us just concentrate on position. So the same information as is captured through this formula may be depicted graphically through this kind of a plot, which we are saying x equals to 5t. This graph may be simply hand drawn, but I would rather recommend you not to draw it with hand, draw it using some computational tools. You should be having access to Microsoft Excel at the least, but I will encourage you to start learning scientific computation tools such as MATLAB or similar scientific computational tools for which you do have access. Okay. So this plot conveys the same information as this, and returning to that, even if it is difficult for you to visualize through this formula, you should readily look at this graph and say, oh, at 500 seconds the position was somewhere here, so that is 500 times 5, which is 50 times 5, which is 250, right. So at 50 seconds I can readily find out the object of my interest is at 250 meters from the origin, right. Similarly, at 1000 seconds I can readily read off the value that my object was at 1000 seconds it is 1000 times 5, at 100 seconds it is 100 times 5, which is 500 meters from the origin. So this graph essentially, even to a layman, should communicate this idea that what is the position of the object at different time, right. So this is very interesting, that whatever you wanted to describe in words, whatever you wanted to describe through a train timetable can be read off either from this graph or through this functional relationship. And at this stage of your learning career, I would rather think that you should use both the formula as well as the graphical representation of it. To give you a little more complicated example, let us take this function. So this time what I have is the functional relationship is in this form. So when t is between 0 to 100, x of t is 5t. So just to concoct a simple example of this situation, or let me run through this formula at this present, and then I will give you an example of how this sort of a relationship does come about. So between t equals to 0 to 1000, x of t is represented by 5t, which means between 0 to 100 I could draw this a 5t graph, which is this red line, right. Similarly, in the next 100 seconds from 100 to 200, the graph, the functional relationship is 1000 to 1000 minus 5t. So in the next 100 seconds I will draw a graph of this. Okay, so this is what is called as a piecewise representation. We have a function for the time interval t to from 0 to 100. We have another functional relationship for the next time interval 100 to 200. We have another functional relationship from 200 to 250, and then we have finally another functional relationship between beyond time 250. So for each of these functional relationships are actually plotted separately, not just in different colors, they are plotted through different parts of the programming. In this case, you could again do it with Excel and look at this plot jointly. Now what does this represent? As I was saying, I can concoct a simple sort of example where this sort of displacement function does arise. Let me take the example of myself. I start from home, which is actually inside the campus, not very far away, but anyway that is beside the point. I start from home, I usually come in a scooter and I ride my, or maybe I come in a bicycle, and my bicycling speed is 5 meter per second, right. So I start from home, which is the choice of my origin for the coordinate system is my home, and this is how the distance from my home keeps increasing for the first 100 seconds. Okay. So my origin is my home, I start cycling, my cycling speed is 5 meter per second, which means that I am covering with every second 5 meters, and in 100 seconds, which is about a little less than 2 minutes, I reach a distance of 500 meters or half kilometers. But then I realized, oh God, I have forgotten the keys of my office. Then what do? I actually start traveling backwards. I mean, I take a U-turn, I don't reverse pedal, but I take a U-turn and actually turn backwards and go towards my home. So in the next 100 seconds, therefore I see that the distance from the origin, remember my home is here, so after having covered gone half a kilometer from my home, I start coming back, and since my cycling speed in the backward travel as I am traveling back home is again the same, in the next 100 seconds I actually reach home, right. So this is the case of my forward travel which has happened over the first 100 seconds. I reach half a kilometer and then I realize, oh God, I have forgotten the keys of my office. So again I come back and I reach my home in exactly 100 seconds. So the distance covered in the forward direction is exactly, sorry, the time taken in the forward direction is exactly same as the time taken in the backward direction, and that is because my bicycling speed in the forward direction is same as the bicycling speed in the backward direction after taking the U-turn, that is. And then in the next 50 seconds I look out where the key is, find it, and then again start. But this time I realize, oh, I am getting late for my lecture, so I actually start cycling faster. So in the next 50 seconds I am actually able to cover 3 kilometers. So look at what happens between 250 seconds to 300 seconds. I have actually covered from 0, I have gone to 3 kilometers. So this entire story I was able to make out looking at this graph. So first I have gone in forward direction, then I came back, picked up the keys from my office. This picking up the key itself took 50 seconds, and then since I was worried that I'll be late for class, I started bicycling faster, and then in the next 50 seconds I was actually able to cover 3 kilometers. So the story apart, what is interesting to note is both the formula and the graph does arise in real application. You may think that this story which I concocted is just a cock and bull story, but there will be cases where you cannot represent the position or against time functional relationship through a single function of the kind that we represented in the first example. You may have to break this up into pieces, and that is why this is called a piecewise representation. It is not possible to give a single functional relationship for the entire period time t equals to 0 to 250 or more in this case, and that is why in individual segments of the time, in the time segments 0 to 100 you have one functional relationship, in the next 100 second period you have another functional relationship, in the next 50 seconds you have another functional relationship. So this is called the piecewise representation, and this is the functional form of it, and this is the graphical form of it. So I would like to sort of conclude here, because maybe tomorrow we will start looking at velocity and accelerations also, and how to derive velocity and accelerations, where we will actually start the formal mathematical calculations. for the other things such as velocity and acceleration. But when you go back home today, please try and practice how to graph different functions. You must by now be exposed to different kinds of functions. You would have seen different functions in your high school. You would have seen different functions in your first semester of your curriculum or even now. So whatever be function, be a functional form of it, let's say cos t, sin t, e to the power t, and different polynomial function t plus t square. The homework that I will leave you with for today is that you should be able to practice how to graph different functions of the kind that I have shown you. If you have access to a scientific computation software such as Maple or MATLAB or Mathematica, it will be very good. But even otherwise, I am quite sure in these days of smartphone technology, everyone carries MS Excel in his pocket. You could either use Microsoft Excel or such similar softwares. But whatever be the software of your choice, please practice how to plot different figures from a given functional relationship. This is extremely crucial and it will serve you a great deal if you can learn this technique well. We have about 5 minutes time. I will be happy to take questions regarding the material presented up to this point. KNMU has asked a question. Even if we are considering acceleration in kinematics, but it cannot be calculated by calculating the net force. That is not true. The way in kinematics we calculate acceleration is that we simply take double derivative with position or derivative with velocity. So if you know the position, derivative of position is velocity, the derivative of velocity is acceleration. The link between acceleration and force is what is called kinetics. So kinematics is about study of position, velocity, acceleration without reference to the forces which is causing the motion. Okay. So if you know the position, you should know the velocity simply by taking the differentiation and doing the calculus of it. If you know the velocity, you should know the acceleration again by a differentiation process. So it is not that you cannot calculate acceleration without knowing the force. You can calculate the acceleration if you know the velocity, for example. So that is the approach we take in kinematics. In kinetics, we relate the acceleration to the force using the inertial properties of mass. I hope that answers the question for KNMU. KNMU, please respond whether you think my answer is satisfactory to you. Okay, SSETN is asking me what is the difference between rectilinear and curvilinear motion. Yeah, I agree that despite my talking, this may sound still slippery, but I'll repeat that once again for you. Rectilinear motion is a motion where to describe the motion characteristics you need only a single variable, but the position, velocity, acceleration are always in one particular direction. It is not changing with time, it is not changing from point to point in space. But whereas in curvilinear motion, the velocity as well as acceleration keeps changing in time. The direction of velocity as the car is moving in a circular track will keep changing according to the direction of the circular direction of the tangent of the circular track, right. So that is called curvilinear motion. Curvilinear motion means it is a particle motion, all points will have the same motion characteristics, but that in curvilinear motion we get to see the fact that the direction, I think I will quickly draw it in board once more just to complete things. So in rectilinear motion you will have a body here at t equals to 0. Since it is a particle, all points have the same velocity, and at a later point also all points have the same velocity, but the magnitude of velocity could be different. This may be a small, this may be a large, but all points is same. So VA, VB, so always VA equals to VB, right, at a later time. And here you have, let's say, VA 0 equals to VAB, sorry, VB 0. So there is no reason that VA 0 has to be equal to VA, but VA has to be equal to VB, but the important thing about rectilinear motion is that even if the magnitude of velocity changes, the direction of velocity is the same. Whereas in curvilinear motion, if it is curvilinear, at a later time, this same body could have velocity in some other direction. Okay, the direction of velocity need not be the same between two different time instants. Whereas in rectilinear motion, the direction of velocity, similarly the direction of acceleration has to be the same for all time instants. I hope I have clarified myself. SSCTN, please respond whether you think your question is clarified. We have time for one more question, hopefully. Yeah, PhD please go ahead.
Sir, good morning, sir.
Good morning.
Your lecture was very nice. Slide number 19, you have shown the comparative figure for rectilinear motion and planar motion.
Just a minute, let me bring that up for you.
Okay, sir.
Yeah, tell me.
Suppose if the first figure, if it is a guard road, so will it come one more variable as the things? Is that direction?
If it is, what did you say?
You have shown some road which is a bend, it's like a hill station. Suppose if it is a guard road, will it come one more variable as a?
Suppose it is what is? Suppose it is a God road. What is God road?
It's a hill road.
Yeah, if it is, if the you mean the road is ascending.
Yes.
Yeah, then it will not remain planar. It could be, you could think that it is a, you need to describe it. You need three variables x, y, and z. The z variable describes the ascent, so that would not remain planar in such case. But as I am also saying to you that if you think that it's a spatial problem and therefore you require three variables to describe it, the other way of looking at it is that even then it could be taken as a curvilinear motion, in the sense that you could follow the path variable instead of looking at a coordinate system which has x, y, and z and trying to map x, y, and z with time. You could always, the driver could always say that I am traveling on this road, and on this road I have traveled a distance 1 kilometer in 1 second, or in 1 hour, 2 kilometer in 1.5 hours, 3 kilometers and such. So such a description in terms of path variable is also possible. Okay, so the number of variables actually does not matter whether it's planar motion or spatial motion. You could describe a plane, just like I have described a planar motion problem in two variables, or I could have used a single variable also in the turning of a car. Similarly, in this case, even though you have brought in the height complication, I could still do that problem using the path variable. Amrita has given me a comment that a better explanation of 100 minus 5t piecewise representation is needed. Well, I'll try that once more. Amrita, can you hear me? Okay, I hope you can hear me. So what I meant by piecewise representation is the following, that you do not have a single functional description which describes, let's say your period of analysis is from time t equals to 0 to 100 seconds, 0 seconds to 100 seconds. And as I talked in my example, that in the first 50 seconds I am going, this is my house and this is my office. In the first 50 seconds I am going in the forward direction, let's say with 5t. Okay, I am going away from my house towards my office at xt equals to 5t. But then I have actually reversed the direction of my motion. I have taken a U-turn and coming back towards my house, and this time my function was xt equals to 100 minus 5t. This was actually 300, I am sorry. So you cannot describe this kind of motion where in the first part of the time you are moving away from your origin, and in the next part of the time you are moving towards the origin. Okay, this cannot be described by a single functional relationship. So it is not possible to describe this motion using a single function. So therefore the best we can do is to describe this part of the motion with one function and to describe this part of the motion with another function, which is what we have done, and that sort of a representation is called piecewise representation. I hope that should be better for you. Kindly Amrita, leave a comment in case you found this supplementary explanation adequate, or you still feel that there is lack of clarity. What is the difference between curvilinear and rotary motion? TKMKL Bini is asking, TKMKL College I believe is asking me what is the difference between curvilinear and rotary motion. See, rotary motion is that which is applicable for bodies. So if I have this kind of body, when it does rotate in this fashion, this is a rotational motion of this body. But now this is not a particle anymore, because different points will have different velocity. The point at this this point, let's say I have a point here and I have a point here. These 2 points are having different velocity as this object is rotating. So therefore this is not a particle. Curvilinear motion is applicable for particles, whereas rotational motion is actually applicable for rigid bodies. Rotary motion, what you are calling it as. So we are going to concentrate here only on particle kinematics, and therefore curvilinear motion is what we refer to in the context of particle kinematics, whereas the rotary motion that you are referring to is applicable for rigid bodies, wherein you have the possibility that different particles will have different velocities. Leave a comment please, TTMKL, if you think that my explanation was satisfactory to you. Okay, in case there are no questions, let's call it a day. We'll meet again tomorrow, and tomorrow we are going to do the velocity and acceleration in both rectilinear and curvilinear coordinate system in a bit more formal fashion. We'll also do some problems on the tab over here. So we'll have a, hopefully you had a good session today. It was pleasant for me. We'll look forward to meeting you tomorrow. Thank you. Have a good day ahead.